Welcome to Pre-Calculus. In this video, we're going to talk about techniques for evaluating limits. So once again, we're talking about evaluating limits without a calculator, without a table of values, and without looking at a graph. And this can be a little bit challenging, but I will say you got to do algebra. I mean, you've got to be good at algebra if we're going to be able to do this. So first, let's start with something that we ended the last video over when we talked about the properties of limits. And this is the direct substitution method. Listen, this should always be applied first. So we've learned all these different properties, but none of them, I mean, I kind of shouldn't be saying that none of them matter, but the point is that the first strategy to find the limit of a function as x approaches a is to simply plug a into the function. Like, that's the first thing you should always do. We call it direct substitution. It's great. It doesn't always work, but listen, if you plug in a and you get a numerical value, then that's your answer. So that's the first thing that can happen. So we talk about the techniques, right? This video is all about techniques. Well, the first technique is direct substitution. And boy, oh boy, if you apply direct substitution, you plug a into your function and you get a numerical value, and 0 is a numerical value. Please, get a lot of kids that get 0 and panic. They don't know what to do. 0 is a number just like 5 or 6. But if you plug your value in and you plug in a and you get a numerical value out, that's your answer. That is your answer. That simply means that you were continuous at A. There was no jumps, no vertical asymptotes, no holes. You were good to go. Now, what else could happen? Well, sometimes direct substitution results in a fraction. And if you get a numerical value divided by 0, well, this actually is also pretty easy. It means your limit does not exist. So if you do direct substitution and you get a number on top, a numerical value on top, and a 0 in the denominator, well, then your limit's quite easy. It does not exist. Because what that means is that you have a vertical asymptote, a VA, I call them. And remember, when you approach a vertical asymptote, you shoot straight up towards infinity or straight down towards negative infinity. So the two sides clearly do not come together, hence the limit does not exist. So listen, direct substitution is so helpful. If you plug a in and you get a number, that's your answer. If you get a 0 in the denominator, does not exist. So pretty simple. Now, the third thing that can happen is where you're going to have some work ahead of you. If you use direct substitution and the result is a fraction with a 0 on the numerator and a 0 in the denominator, then, oh boy, first, this means there is an answer. Okay, there is an answer to your limit. The limit does exist, but we're going to have to do some good algebra work to find that answer. So I call it the dreaded double 0. So just understand that when you get a 0 over 0 with direct substitution, that's where you're going to have some work ahead of you. But other than that, the other two things that can happen are you get a number. Well, if that's the case, that's your answer. If you get a 0 only in the denominator, well, then your answer does not exist. And if you get the dreaded 0 over 0, that's when you're going to have to do some work. But listen, I can't say enough. You should always start with direct substitution. That should be the first technique, the first strategy used if you're trying to evaluate a limit without a graph or calculator. Okay, but listen. I've already said it. I'm going to say it again. Always, always, always try direct substitution first. If you get that dreaded 0 over 0, then you are going to have some algebra work ahead of you. And that algebra work could come in several different flavors, several different techniques. And that's what this video is all about, is kind of teaching you those different techniques to help you in that situation. Any other situation is easy. The only situation that's tough is the 0 over 0 situation. All right, so without further ado, let's get our hands there. Let's do some examples. So in this first example, I'm asked to find the limit as x approaches 1 of a pretty nasty looking function. But listen, first strategy you should always apply is the direct substitution, which means I'm going to plug my a value, which in this example is 1, into the function. So I get 1 cubed minus 3 times 1 squared plus 7, all divided by 2 times 1 minus 5. All right, let's see here. 1 cubed is 1. 1 squared is 1. 1 times negative 3 is negative 3, plus 7. 2 times 1 is 2, minus 5 in the denominator. So let's see here. On top, 1 minus 3 is negative 2. Negative 2 plus 7 is 5. And the denominator, 2 minus 5 is negative 3. Hey, I applied direct substitution, and I got a numerical value. My answer is -5/3. I don't have to do any more work. That's it. That's my limit. The limit as I approach 1 is -5/3. How easy was that? Guys, come on. All right, let's try this next one. Once again, a weird, crazy-looking function, but listen, they want me to approach a, so why don't we just direct substitute a in and see what happens. So if I plug in 2, I get the square root of 2 plus 5 minus 4 on the outside. Let me clean that up a little bit. On the outside, I don't want to make sure the 2 plus 5 is on the inside. The minus 4 is on the outside. All divided by 2 minus 2. All right, so 2 plus 5 is the square root of 7, which is not a very nice number, minus 4. Now, again, square root of 7 minus 4, that's a number. I could go to my calculator right now and get that number. All divided by 0. Okay, so essentially I'm going to get a number in the numerator and a 0 in the denominator. Okay, now the number in the numerator is not very pretty, but it's a number. The most important thing is, though, I get a 0 in the denominator. Remember, that makes it pretty easy. That means does not exist. Now, I know we don't have a graph in front of us, but what this means is at 2, there's a vertical asymptote. And when you approach a vertical asymptote, you're either going to go straight up or straight down forever. And that means that the limit does not exist at 2, or as we approach 2. So again, these are 2 examples of when something really nice happens. You get a number, you're done. You get a 0 only in the denominator, you're done. The answer does not exist. All right, so let's look at some examples where we do end up with the dreaded 0/0. Now, I'm not going to do any more examples like these ones because they're easy, right? I mean, you just have to understand what direct substitution means. You plug the number in. If you get a number, you're done. That's your answer. So I don't want to do 15 more of these because it's pretty self-explanatory. But what I want to look at is that dreaded 0/0. So here's an example. All right, so the first thing I'm going to apply is the direct substitution. I'm going to plug 3 in just to see what happens. So I have 3 squared minus 3 minus 6 over 3 minus 3. Clearly, that's a 0 in the denominator. Let's see, the numerator is going to be 9 minus 3 minus 6. 9 minus 3 is 6. 6 minus 6 is 0. So again, I get that dreaded 0/0. Now, you have to understand, this means there is an answer. This limit will have an answer. I just got to do some algebra to find it. Now, the technique I'm going to use here is the divide out, the cancel out technique. So what happens is that, let me factor everything. So if I factor the numerator, I get x minus 3 times x plus 2. If you don't believe me, just double check my work there, but -3 times 2 is the -6. Inside's a -3x, outside's a +2. That makes the -x in the middle. I'm not going to reteach factoring. You guys should know that. Now, here's what's awesome, right? After I factor, I realize, oh, I could cancel out the x minus 3s. Because an x minus 3 in the numerator and x minus 3 in the denominator, those factors, if they're exactly the same, are going to reduce to a 1. So essentially, I just turned this limit into the limit of x plus 2. So after I cancel out those x minus 3s, all that's left is x plus 2. Now that you canceled out the problem, replug 3 back in. So now the idea is once you cancel something out, this is the cancel out technique, once that something cancels out, then do direct substitution again. 3 plus 2 is 5. You're done. There's your answer. So, sorry, but that was pretty easy. I hope you agree. So again, if you have a rational function, numerator, denominator, and you get that double 0, go ahead and factor. Something will cancel, I promise. Once that cancels, redo direct substitution, and you'll have your answer just, I'm trying to snap my fingers right now, just like that. You'll have your answer just like that. All right, let's try another example that uses a little different strategy. So notice the first thing I'm going to always do is plug 0 in. And in that case, I get 4 plus 0 in the square root, minus 2 on the outside, all divided by 0. So obviously, that's a 0 in the denominator. Now, in the numerator, the square root of 4 is 2. 2 minus 2 is 0. So once again, I get that dreaded double 0. Keep in mind, this is actually, in a sense, it's a good thing because it means there is an answer. I just have to do some work to find it. Now, the answer here is going to be rationalizing. Essentially, we want to try to get rid of the square root. And it's actually going to work, kind of, but not really, but you're going to see my strategy here. So I'm going to start off with the original problem, 4 plus x minus 2, all divided by x. And the strategy here is to multiply by the conjugate, okay? Now, if you're not familiar with the word conjugate means, I'll just do a quick side lesson here. The conjugate of A plus B is simply A minus B, right? You don't change A, you don't change B, you just change the sign in between. So what's the conjugate of x minus 2? X plus 2. What's the conjugate of x squared minus 4? X squared plus 4. So again, what we're going to do here, the strategy is just to multiply by the conjugate. So that would be the square root of 4 plus x plus 2. Notice that I did not change the square root. I did not change the 2. I just changed the sign in between. But algebraically, if I multiply the top, I got to multiply by the bottom by the exact same thing. So essentially, I'm multiplying by 1 because anything divided by itself is 1. And if you multiply by 1, you might change what you look like, but you don't really change what you are. So you're going to see how this is going to actually work out really, really nicely. So once again, it's whatever that square root is. When you see that square root, you want to multiply by that conjugate involving it, okay? Now, things are going to get a little bit ugly here, but they'll clean up pretty quickly. So I'm going to multiply the numerators together, and those are a binomial times a binomial, so I'm going to multiply the square roots. So what's the square root of 4 plus x times the square root of 4 plus x? Well, when you multiply two square roots that are identical, the square roots cancel, and you just get 4 plus x. Pretty simple. Then I'm going to multiply the inside and the outsides. Now, this is super important as to why I chose the conjugate. When you multiply two conjugates together, you automatically get the inside and the outside terms to cancel, which is exactly why I am doing this technique. Anytime you multiply conjugates together, two things that are only different by the sign in between them, they're always going to cancel out those inside and outside terms. And just to prove that to you, look what happens here. On the outside, I get 2 square root of 4 plus x. On the inside, I get negative 2 square root of 4 plus x. They're the exact same thing, but one is positive, one is negative, so they're going to cancel. So I'm not even going to worth writing them down because they're just going to cancel out. If you need to write them down, go ahead. I'll do it very quickly here. But on the outside, I get positive 2 times the square root of 4 plus x. On the inside, I get negative 2 times the square root of 4 plus x. And those are just going to cancel each other out and make 0 anyway. And then don't forget about the last terms. Negative 2 times positive 2 is negative 4. Now, in the denominator, honestly, don't do anything. Just leave x times the conjugate of 4 plus x plus 2. I mean, you just really can't do anything there. I guess you could distribute it and get x square root of 4 plus x plus 2x, but it's actually not worth your time to do that. Now, what happens in the, and you're going to see why. Just watch what happens, right? The 4s are going to reduce to a 0. 4 minus 4 is 0. So I have x over x times the square root of 4 plus x plus 2. But now look what happens. I have an x in the numerator and an x in the denominator. Those are the same factor. So if x is 5, I got a 5 over 5. That's 1. If x is 17, I got 17 over 17. That's 1. So this x and this x are going to reduce down to a 1. And essentially, I get 1 divided by the square root of 4 plus x plus 2. So listen. What did I do? I took the original function and I multiplied it by the conjugate over itself. So essentially I was multiplying by 1. So yes, I'm changing how it looks, but I really haven't changed it. And this is my final answer. So this final answer is actually no different. This limit, 1 over the square root of x plus, well, I'm going to write x plus 4. It's the same thing as 4 plus x. It's addition, order of addition doesn't matter, plus 2. So again, I know that these two functions look different, but they're actually not different at all. All I did was multiply by 1, so I changed how it looked, but didn't really change it. And the strategy here is awesome because doing this, let me erase this to give myself some room. Doing this, I know it looks different, but it's now going to allow direct substitution to give me an answer. So again, once you got something to cancel, which again I did, I got these x's to cancel. Now I'm going to directly substitute 0 back in. And this time I get the square root of, well, 0 plus 4 is 4. So I get the square root of 4 plus 2. The square root of 4 is 2. So I get 2 plus 2. And that is 1/4. So there's your answer, 1/4. So what's happening here is, what do these last two problems have in common? Is that there was an answer, but it was just disguised. And you had to change how the problem looked to make it undisguised. So in this previous problem, what I did was I factored and canceled. So again, I made it look different, but not really be different. And then I direct substituted to get my answer. In this problem, the strategy was to multiply by the conjugates on top and bottom. And again, what happened, it looked different, but it really wasn't different, even though it looked different, but allowed direct substitution to get me that answer of 1/4 really, really nicely. So when you see square roots, and okay, first off, always try direct substitution first. When you get that 0, 0, and then you say, okay, I got a square root. What do I do with the square root? That's when you use this conjugate method. All right, one more technique for double fraction problems. All right, so first, again, always try direct substitution. It annoys me when kids say, I don't know what to do. Well, did you try direct substitution? So I'm going to plug 0 in for x. 0 plus 3 is 3, so I get 1/3 minus 1/3, all divided by, well, turning x into 0 results in 0. So the numerator, 1/3 minus 1/3 is 0. Denominator is already 0, so there's that dreaded 0 over 0. Again, good news is there's an answer. Bad news is I got to do some work to figure it out. So once again, here's what we're going to do here. This is a strategy that's very, very simple. So I'm going to start off with the original function, which is a really ugly function. And I'm going to try to make this one giant function. So that's the strategy. Make it look like one function. So the first thing I got to do is I got to combine the top together. So I do need to get a common denominator on the top. So my common denominator is going to be 3 times x plus 3. So this first fraction needs the 3, so I'll gladly multiply top and bottom by 3, which is going to generate 3 times 1 is 3. This back fraction needs the x plus 3. I'll gladly multiply the numerator and denominator by x plus 3, so that way I get the common denominator. Just be careful though, there's a negative sign that needs to come along with this one, so I get negative x and a negative 3. Please be very, very, very careful with that. I'm begging you. All right, now here's what else I'm going to do at the same time, right? Instead of dividing everything by x, making a double fraction, which I hate, let's multiply by the reciprocal. The reciprocal of x is 1 over x. Okay, so what did I do? Well, essentially all I did was got a one fraction in the numerator by getting a common denominator, and then instead of dividing by x, which makes that ugly double fraction, I multiplied by the reciprocal 1 over x. Now, let's see what happens. First, in the numerator, the positive 3 and the negative 3 cancel out, so I just get negative x over 3 times x plus 3 times 1 over x. Uh-oh, look what's going to happen. The factor of x and the factor of x are going to cancel. Again, x divided by x is 1, so again, it's just canceling, it's just gone. 5 over 5 is 1, 10 over 10 is 1, x over x is 1, so it's gone. So all that's left is a negative 1, don't forget about this negative right here, divided by 3 times x plus 3. So it's actually very similar. It's a different technique, but very similar to the previous two problems. I did something that made the function look different, but not really be different. So now this original problem can now be looked at as the limit as x approaches 0 of negative 1 over 3 times x plus 3. Now that I got those x's to cancel, I'm going to plug 0 back in. I'm going to go back to direct substitution. And I get negative 1 divided by 3 times 0 plus 3. Well, 0 plus 3 is 3. 3 times 3 is 9. So there's my answer of negative 1/9. Oh boy. Okay. So when you do get the dreaded 0 over 0, that means you have some algebra work ahead of you. That work typically comes in 3 forms, but they all result in the same strategy, getting something to cancel. So if it's a fraction like this, where you have a rational function, you're going to factor, you're going to see a common factor cancel, and then you have a new function that looks different, but it's not different. Plug your direct substitution in, and you'll get your answer. If you have this problem with square roots, the strategy is to multiply by the conjugate. Kind of a weird strategy, but trust me, it will always work. You just have to practice it. Once you change how the function looks without really being different, then you reapply direct substitution and you'll get your answer, 1/4. And then in this problem, the double fraction problem, once again, the strategy is to combine it all to a single fraction. So I had to combine the numerator to a single fraction, and then I multiplied by the reciprocal to get rid of the dreaded ugly double fraction. And then something really nice canceled, those x's canceled, and then I plugged direct substitution back in to get my answer. And again, these are the 3 techniques that are going to work. I'm telling you, they will always work. They're really, really nice. All right, now I am going to have a follow-up video to this with just more examples. So if you're like, boy, I could really stand to look at a couple more, I would highly suggest looking at that video. But I do want to look at a couple problems with piecewise functions. Piecewise functions are some other problems that oftentimes kind of fool kids. But listen, just apply direct substitution and you're usually going to get the answer right. All right, so let's find 5 different limits. Now, this is a piecewise function where I use 4 minus x if x is anything less than 1, or 4x minus x squared if x is anything greater than 1. All right, so the first question wants me to find the limit as x approaches -5. So again, I'm going to use direct substitution. Just plug it in, right? That's the new strategy. Just plug it in and see what happens. But where do I plug it in? Well, -5 is less than 1, so I'm going to plug it into the top function. So I do 4 minus -5. That results in a +9. Hey, that's a number. If you get a number, that's your answer. How easy was that? All right, let's do this next one here on the bottom. What is the limit as x approaches 7? So once again, direct substitution says plug it in. But where do I plug it in? Well, 7 is greater than 1, so I'm going to plug it into this second one. 4 times 7 minus 7 squared. 4 times 7 is 28. 7 squared is 49. 28 minus 49 is -21. Hey, that's a number. That means that's my answer. All right, now these next two want us to look at approaching 1 from the left, from the right, and then overall. So let's see here. Let's approach it from the left. So if I'm approaching 1 from the left, that would be something lower than 1. Lower than 1. Less than 1. So that would be using this top function right here, because this top function is when you are less than 1. So I'm going to plug 1 into there. 4 minus 1 is 3. So voila, there's my answer, right? Direct substitution. The only issue is how, 1 is like the line. 1 is where we switch between the two functions. So how do I know which one to plug it in for? Well, if I'm looking to approach from the left is less than 1. So that's why I plugged it into here. 4 minus 1 got me 3. That's an answer. All right, what about approaching 1 from the right? Well, from the right of 1 would be numbers greater than 1. So I'm going to plug it into this second equation here. And I'm going to just see what happens. 4 times 1, is 4. 1 squared is 1. 4 minus 1 is 3. Okay, how awesome was that? So when I approach it from the left using the left function, I got 3. When I approach from the right using the right function, I got 3. And since they're the same, remember, we learned this in another video over one-sided limits. If the left side and the right side are both coming together at the same value, then that answer is also your overall limit, because the overall limit says what happens if you approach from both sides. And as I approach 1 from the left and from the right, and they both equal 3, well, then I got my answer. All right, one more example of problems here, another piecewise function. This time, I have 2 options for where I'm greater than 2 and where I'm less than or equal to 2. So be careful, I kind of switched the order up here. The top is greater than 2. The bottom is less than or equal to 2, okay? So just make sure you pay attention to those signs. All right, so the first limit wants me to explore what happens if I approach 4. 4 is greater than 2, so I'm going to use this top equation. 3 times 4 plus 2. That's going to be 12 plus 2. 12 plus 2 is 14. That's a number. That's my answer. All right, what about approaching -1? Well, once again, -1 is less than 2. So I'm going to use that bottom equation. 2 times -1 squared minus 5 times -1. -1 squared is 1. 2 times 1 is 2. -5 times -1 is +5. 2 plus 5 is 7. Hey, 7's a number. That direct substitution tells me if you get a number, that's your answer. All right, now this next one's a little tricky, so bear with me here. But they want me to approach 2 from the left. Well, left is less than 2, right? Left is less than 2. So that means I'm going to use this equation that is less than 2. So that's going to be 2 times 2 squared minus 5 times 2. Let's see here. 2 squared is 4. 4 times 2 is 8 minus 10. 8 minus 10 is -2. So from the left of 2, I'm approaching -2. All right, now I want to approach 2 from the right. The right is greater than 2, so I'm going to use this top equation for greater than 2. So that's going to be 3 times 2 plus 2. 3 times 2 is 6. 6 plus 2 is 8. And, okay, great. The left side is at -2. The right side is at 8. Well, what does that mean for the overall limit? Does not exist, right? If the two sides aren't coming together, then the limit does not exist. So that's another great example. So it's pretty much just following the directions of the problem, right? Whatever you're approaching, just make sure you plug it into the right equation, the one on top or the one on the bottom. You got to read to know which one. And if you want to approach the number that's like the cutoff, so in this example, 2 is the cutoff where we switch functions, just make sure you choose the right one, because if you want to go from the left, you want to use the one for less than 2. If you want to go from the right, you want to use the one for greater than 2. I mean, it's really that simple. All right, so once again, I want to remind you guys there is going to be a follow-up video to this with some more examples, especially of these problems where you get the dreaded 0 over 0. These are the 3 techniques that you're going to see most often. But I want you, the more examples you see, the better you're going to be at it. But these are the same techniques, the divide and cancel technique, the conjugate technique, or the double fraction technique. So be ready for some more examples of that in the next video if you need them. All right, guys, so that's how you evaluate limits with algebra. Notice I never once touched a calculator. I never once looked at a graph. I used basically direct substitution. And the only time you ever have to sweat it out is when you get the 0 over 0. And when that happens, you just got to make sure you apply one of these strategies to change how your function looks without actually changing what it is. All right, love you guys. If you need to watch that video with extra problems, please do so.